Welcome to the Seas Roving the Red Planet team presentation. Our mission was to plan a Mars ISRU reconnaissance and experimentation mission, or MIREx for short, that proves the viability of ISRU processes and sets up infrastructure for future manned missions to Mars.
So moving to background information for our mission, as Rachel said, our proposal mainly revolves around using ISRU, or in situ resource utilization. And ISRU essentially means extracting minerals from the surface of a planet and using them to create resources that are useful to humans. So in our case, this would be extracting minerals from Mars and using them to create water, oxygen, and other things that would be useful for humans. So with that in mind, our three main mission objectives are one, to create advancements in ISRU, astrobiology, Martian geology, and proving our ability to build infrastructure. So in the future, when manned missions build infrastructure on Mars, we want to prove that we have the ability to create bricks and other useful materials for infrastructure. Our second goal is to study the Martian climate through data that our rover collects. That way we can find sites that will be suitable for these future manned missions. And lastly, we want to search for indications of past life, and this is done through biosignatures on Mars's surface.
We selected Mawrth Vallis as our landing site. It is located next to a channel that was formed from one of the massive floods on ancient Mars. As a result, this site contains large quantities of clay minerals that can be used for building, as well as potentially contain insights into the past of Mars. One of the great things about this site is the high levels of phyllosilicates. Studying phyllosilicates deposits can help us identify biosignatures in our search for ancient life on Mars. Additionally, there is some interesting morphology at this site, and there are also lots of aluminum and iron magnesium clays in this area. The high levels of hydrous minerals could provide useful material for ISRU research, as well as constructing structures for future manned missions. Finally, Mawrth Vallis was chosen as it is a good representation of large areas of Mars. Similar meteorological data has been seen across large areas of the Red Planet, hundreds of miles away, meaning that preparations and discoveries made in Mawrth Vallis can be largely applied to vast regions across the rest of the planet.
Our rover has two goals: to discover evidence of past life on Mars and to prepare for future human missions. Our rover is equipped with 4 different instruments: the Rover Environmental Monitoring Station, a 3D printer, a supercam, and the Sabatier reactor. First is the Rover Environmental Monitoring Station, nicknamed REMS. REMS is an onboard weather station comprised of 3 parts. Sensors on the rover's body measure ultraviolet radiation and air temperature. One sensor within the chassis analyzes atmospheric pressure, and 2 booms extend from the mast to evaluate ground temperature, wind speed and direction, and humidity. At each of our targeted sites, we will systematically record climatic data and examine the day-to-day weather patterns. The information collected will enable scientists to determine the optimal site for future human operations.
The next instrument our team selected was SuperCam. The image on the slide shows SuperCam's mast unit prior to its installation on the Perseverance rover. SuperCam can work from distances of greater than 7 meters or 20 feet away and can study targets as small as a pencil point. It identifies the chemical and mineral makeup of rocks and soil using a camera, laser, and visible infrared spectrometers. Roger Waynes, the principal investigator, is quoted saying that SuperCam's laser is uniquely capable of remotely clearing away surface dust, giving the instrument a clear view of the targets. We expect to use this device for the mineralogical mapping of Mawrth Vallis, which will give us a deeper geologic insight into the area and help with mission planning and development. It will also help in the search for preserved biosignatures and will help accomplish our ISRU objectives and the study of Martian regolith.
Another instrument that we will be adding to our rover is a 3D printer arm. To use the 3D printer arm, the rover will extract a small sample of the Martian regolith using a scoop and identify the mineralogical composition using SuperCam. The regolith will then get mixed with water and a binder to create a cement mixture. The 3D printer would then take the cement mixture and print a small 10 by 10 by 10 centimeter structure on the Martian surface and take photos of it over the course of a week to ensure that it's set right and to monitor any wear that the structure may experience in the Martian weather. Using this, we expect to gain a deeper understanding of how different minerals react in a 3D printed context, and we expect to understand what the most beneficial minerals would be to create a 3D printed Martian structure.
The last instrument that we'll be putting on our rover is a Sabatier reactor, which is a small device that takes in CO2 and hydrogen in order to produce water and methane via the equation shown. In addition to that, a catalyst can and will be used in order to increase the efficiency of this reactor. Now let's move to the expected value of this reactor. For our ISRU purposes, we expect to use a reactor similar to the one built in the NASA George C. Marshall Space Flight Center. This reactor was 8 inches long and 1 inch in diameter and could expect to run at a temperature of 250 to 450 degrees Celsius with an intake gas ratio of 3.5 to 5.5 hydrogen to CO2 respectively. Furthermore, this design has withstood many vibrations without losing efficiency, which is very important to us since our rover will be moving over relatively uneven terrain, which can cause slight movements in the instruments. Lastly, let me talk about some devices that will be needed in order to make this reactor work. First, a soil collection device will be needed in order to gather the hydrous minerals needed. And then a soil treatment device and vapor extraction device will be needed in order to extract the trace gases from these said minerals. Now let's move to the geological maps.
This is our first geologic map, which displays the hydrous mineral detections around our study area Marth Vallis. Each hydrous mineral that will be useful for ISRU is indicated by its corresponding color, which you can see on the right. Each mineral displayed has an important role in our mission. Hematite is useful for radiation shielding in addition to providing iron to use as a building material. Hydrated sulfates are a useful source for ISRU water extraction. Feldspar and phyllosilicates will help our astrobiology studies as these minerals can contain preserved biosignatures and provide insight into Marth Vallis' history. And last but not least, hydrous minerals are useful for ISRU water extraction.
Another useful mineral in our Marth Vallis study area is basalt, as there are large abundances of basalt on Marth Vallis. The basalt abundances could allow us to look into the history of our site. Additionally, basalt provides the benefit of being used as an ISRU construction material, as it is used for road base and concrete aggregate on Earth.
Now, onto our Rover Traverse route, where the team had to consider both the mission objectives and rover safety. This is the traverse trail our team formulated. The map is at a 5-kilometer scale for reference. The speed at which the rover travels is dictated by the terrain it needs to rove. This was calculated using previous data according to safe rover speeds on various Martian terrains, meaning that the site location was not the only factor that went into designing the best route. We analyzed the rock abundance from the TES data from JMARS, as well as slope data and elevation to finish the map. Additionally, it should be noted that we plan to land the rover in the westmost point of our overall studied area at Marth Vallis to be able to best study the delta deposits. This means that the rover is always moving closer to the channel. This takes into account the trend of the graph above to the left, that is, the continued lowering of elevation throughout our planned course. Even when exiting the crater we enter in Site 3. The map to the right gives a greater view of elevation changes. Blue depicts low elevation and green high or the regular elevation of the area.
The first traverse segment includes one super high importance site and another medium importance site. These importance levels were determined based off how each site addressed our mission objectives. The first traverse segment data on the slide excludes the time they would take for the rover to land and move into the site. However, that being said, it would take around 17 days for the rover to traverse this segment. At Site 1, we will spend 8 to 10 days studying how the gypsum and olivine at the site react in a 3D printed context, as well as studying the phyllosilicate deposits at the bottom of the crater and scanning for biosignatures. The MIREx rover will also begin to use the REAM instrument to take detailed climatic readings of the region. To accomplish these goals, the MIREx rover will take advantage of the SuperCam, REAMs, and 3D printer instruments. Site 2 is a medium importance site, where the rover will use the SuperCam instrument to study the mineralogical differences between the light rocks of the valley and the dark rocks of the crater. Additionally, the rover will use SuperCam to identify any interesting minerals in the crater rim. The rover will continue to take detailed climatic readings at Site 2 and will leverage the REAMs and SuperCam instruments.
The second traverse segment of our rover begins at the site of high importance and ends at the site of low importance. The segment of our mission will take 18 days. When the rover arrives at the third site, we use a SuperCam to take a detailed mineralogical map of the site. Additionally, the SuperCam will identify and study the chemical and mineral deposits of the site, such as the abundance of perfluorites. For Site 4, the rover will focus on recording Martian climate. The REMS will be used to achieve this task. The SuperCam will also be used to make a mineralogical analysis map, will be much less in-depth than the map made in Site 3.
After 185 hours of roving, we will arrive at Site 5, where we plan to spend 2 to 3 days recording weather conditions and creating a detailed mineral map. After another 140 hours of roving, we will arrive at Site 6, where we plan on spending a day doing similar objectives. After another 81 or so hours, we should arrive at the final Traverse segment, Site 7, where we plan on spending a long time, in this case 8 to 10 days. Here we plan to search for biosignatures and 3D print a structure.
Because one of the major goals of this mission is to prepare for future human missions to Mars, we have to make sure to take human health considerations into account. These considerations include certain harmful chemical compounds found within the Martian environment, as well as severe climate conditions that could potentially cause harm to human health. Perchlorates are one chemical compound that can be found within Martian soil at concentrations ranging between 0.5 and 1%. At these concentrations, perchlorates are known to be dangerous to humans and can cause disruption of thyroid gland function. However, perchlorate exposure is generally only harmful when it's ingested through contaminated food or water. The risk of harm through skin absorption or inhalation is relatively low, which means that if proper precautions are taken, perchlorates in Martian soil are not likely to cause severe adverse effects in humans. Perchlorates also have possible ISRU benefits, such as the creation of oxygen and rocket fuel, which means it's even more important to be able to handle them in a way that won't harm human life.
Silicates, which are present in Martian dust, are known to be toxic to humans. In a fine dust, they are even more dangerous as they can freely enter the body and eventually the lungs through airways. One of the risks associated with silicates is silicosis, which occurs when silica enters the lungs and induces scar tissue formation. This in turn impairs one's ability to breathe in oxygen, making the disease very dangerous. Some additional adverse health effects of silicate exposure include lung cancer, COPD, and kidney disease. The Martian climate can also be detrimental to one's health. For example, humans may not be able to withstand extreme temperatures on the planet, which can reach as low as negative 125 degrees Celsius in the wintertime. Additionally, the Martian atmosphere blocks less harmful UV radiation from the sun than Earth's atmosphere. Although the overall UV fluxes the two planets receive are similar, the shorter wavelengths on average, which comprise much of the UV radiation exposure on Mars, are even more damaging to humans than those on Earth. Yet another area of concern is Martian dust. Due to the fine particle size, it is easy for it to be ingested. Some measures of protection against dust that are being considered include self-cleaning spacesuits and the construction of obstructive structures.
On behalf of the whole Roving the Red Planet team, I would truly like to thank everyone at SEAS for making this possible. And to do that best, our team would like to address the benefits we felt the SEAS has had on us. To put it simply, we thought SEAS was an amazing experience that allows for each and every one of us to connect with like-minded peers in a way we have never felt we have before. Not only that, but we can all agree that having the chance to work with professionals in our fields of interest was perhaps the best form of learning we could have received. With that being said, it wasn't always easy. Almost immediately, obstacles arose. One of the first was time zones problems. However, we quickly resolved this with frequent and pre-planned meetings where we could simply chat, work, or check in. Now, a little bit of a closer look at what everyone thought about their intern experience.
Fortunate for the experience and to walk away with so many important skills that we have learned through the completion of this project, such as collaboration and research that we will carry with us into the future of our careers. The SEAS program has expanded our passion for STEM and has exposed us to many new fields of science that we haven't engaged in before. SEAS has also given us insight into the wide variety of careers and fields that we can apply our passions to, and has shown us how our passions correlate into solving a real-world problem. The SEAS program has given us many new experiences that have improved who we are as researchers and scientists, and we have gained many valuable connections that will help us in our future of our careers in research and science. We are also thankful for the ability to collaborate with like-minded individuals that has overall expanded our desire to learn and has increased our knowledge of Mars.
That is our presentation. So from the whole Roving the Red Planet team, we would like to say thank you for this excellent opportunity and thank you for watching our presentation. Are there any questions?